Ok, ahora sí, ya estamos grabando.
Muy bien.
Buenos días, buenas tardes y buenas noches, porque Bruce está en Japón y Neven está en Suecia y los demás compañeros casi todos están o en Estados Unidos o en México. En esta ocasión me da mucha alegría presentar a nuestro ponente, Neven, el doctor Blaskovich. Estudió en Oxford por un largo periodo de tiempo. Obtuvo su licenciatura y su maestría conjuntas en el 2011 y después hizo su doctorado, que lo obtuvo en el 2015. Del 2015 al 2017 estuvo como postdoc ahí en Oxford también. Después de eso fue Senior Fellow en el CERN del 2017 al 2019. Después hizo otro postdoc en el ISS, en European Spallation Source, en Suecia, del 2020 a 2021. Y desde el 2021 está trabajando como investigador en el Max IV, en el laboratorio Max IV de la Universidad de Lund, en Suecia también. Y hoy nos va a platicar sobre el trabajo que hizo durante su investigación doctoral. En esta ocasión, el doctor Blaskovich escogió dar la charla en inglés, lo que me parece bastante bien también para que los compañeros tengan un poco de variedad entre charlas en inglés y en español. Sin embargo, si hay preguntas, me parece que pueden ser tanto en inglés como en español. Y sin más, le voy a dar la palabra a Neven. Voy a apagar mi cámara. Sí,
Muy bien. Yo voy a intentar compartir la pantalla. No sé si veis la pantalla correcta.
Perfecto.
Vale, sí, como dijo Alex.
Sí, se ve.
Perfecto, muy bien. Como dijo Alex, presentaré en inglés porque hice todo mi trabajo en inglés y entonces me salen las palabras en inglés. Pero también, como dijo Alex, cualquier pregunta podéis preguntar en español, ningún problema. Y también, antes de empezar, daros las gracias por darme la oportunidad de presentar. Y además, Alex y yo nos conocemos ya desde hace 9 años y es un placer poder presentaros mi trabajo del doctorado. Pues empiezo entonces en inglés. So the presentation today will be about beam position feedback systems for linear colliders. This is the work that I did during my PhD in Oxford, and I am currently based at Max IV in Lund. So for my PhD, I was developing feedback systems to control the beam trajectory of electrons in an accelerator. And this was done as part of the FONT group, and FONT stands for the Feedback on Nanosecond Timescales group, which is a group at Oxford University led by Professor Phil Burrows, who's also my PhD supervisor. So the outline for this talk is I will first introduce the concept of linear colliders, and then the feedback systems that are required for these linear accelerators. I will introduce the machine at which we did our experiments, which is the Accelerator Test Facility in Japan. I will show the experimental setup that we used in order to operate the feedback, and then the results that we obtained there. So a future electron-positron linear collider could be used, for example, as a Higgs factory. So the Higgs particle has a mass of 125 GeV, which is a unit of energy or mass. And therefore, in order to produce the particles, we will need 250 GeV collision energy. But these linear colliders can produce higher energies, up to 1000 GeV, which is 1 tera-electron volt, or even up to 3 TeV, depending on the design of the machine. So at present, there are two consolidated designs for linear colliders. The first one, which is the one I will mostly talk about, is the International Linear Collider, ILC, which is proposed to be in Japan. Another design, which is also has extensive research, is the Compact Linear Collider, CLIC, which is proposed to be on a site at CERN in Geneva, in Switzerland. So as I said, the International Linear Collider is an electron-positron collider that is proposed to be built in the future in Japan. Depending on the size of the linear accelerator, it will be able to accelerate, it will be able to achieve a center of mass collision energy of between 250 and 1000 GeV. I point out the very small beam size that we have at the collision point, which is only 6 nanometers, because by concentrating the particles into a small spot, we can get many electron-positron collisions, which are necessary in order to analyze the outcome of those collisions. So the schematic on the bottom shows the accelerator design for the ILC. You can see that there's an electron source here in blue, and then the electrons go into these rings because that allows us to reduce the size of the beam. We always want to have a small beam. And then the electrons go to the start of the linear accelerator and are then accelerated. The electrons themselves can be used to produce positrons, which are shown in green here, which then follow a similar path to the opposite end of the accelerator, and then they are accelerated towards the electron beam, and then the collision happens in the middle. So I will now introduce why we need a feedback system. So first of all, achieving the collisions is going to be very hard. The reason it is hard is because, as I said, the beam is very small. It's only a few nanometers high. And because the ground is continuously vibrating and all the elements in the accelerator are vibrating by a few nanometers every second, then you can see that very quickly the two beams that we are trying to collide will be misaligned, and then they will miss each other. And this takes me to the second bullet point over here, which is that it is very important to achieve the collisions. And the reason is that linear accelerators are single pass. This means that the particles go only once, and once, if they miss each other, then the beam has been lost. So it's very important to achieve successful collisions first time round. And also, we want the two beams to collide head on. And the reason for that is because it maximizes the overlap of the two bunches, and therefore it maximizes the number of collisions between the two beams. So the solution in order to achieve these collisions is to have a very fast feedback system which corrects the beam positions of the two colliding beams. At this point, it is worth explaining the structure of the beam inside the accelerator. So the beam is made up of bunches. These are just collections of around 10 billion electrons in each bunch. And these bunches are accelerated with a bunch spacing of around 500 nanoseconds. It's a very short interval of time. And we have 1,300 bunches for the ILC, which constitute one train. And then we have a long pause of 1/5 of a second until the next train of bunches arrives. So the challenge, because all the elements in the accelerator will be misaligned after around a second, we need to be able to correct from one bunch to the next bunch in order to prevent the accelerator from misaligning too much. So the important message over here is that we need to act fast, and we need to correct from one bunch to the next before the accelerator has misaligned significantly. So the way that a critical feedback system would work at the ILC is known as the interaction point feedback. So the interaction point is the point where the two beams collide. And you can see in this schematic over here, I show the two beams. For example, the electron beam maybe in blue and the positron beam here in green. And you can see that when they collide, so there's a small angle between them because we need to get them into collision, and then we need to be able to extract them and direct them towards a dump at the back. But the important thing here is that if the two, so the collision angle has been greatly exaggerated here. The two beams are almost going parallel to each other. And if the beams collide exactly head-on, then there will be no overall deflection because everything is perfectly aligned. But if the two beams are slightly off-center, then because there's a strong electric force between the positive positrons and the negative electrons, these opposing bunches will attract, and then the two beams will be deflected because they will be attracted to each other. So what we will do is we will measure this deflection on the outgoing beam from the collision. So on this outgoing blue beam, we will put a BPM, that is a beam position monitor, and we will have to have some processing electronics in order to extract the information from the BPM and then process this information in order to calculate a correction that then needs to be applied to a kicker on the other beam. And you can see that reading in the data, processing the data, calculating the correction and applying the correction has to happen very quickly in the time interval that we have between one bunch crossing and the next bunch crossing 500 nanoseconds later. So that is one type of feedback where we use one beam position monitor and one kicker. Now I will explain a different type of feedback system which will also be present at such a machine. This feedback system corrects both the position and the angle of the beam. So this is a distributed type of feedback in the sense that once the position and the angle of the beam are corrected, then this correction should propagate down the accelerator. In order to achieve the correction of both the position and the angle, we require at least 2 BPMs and 2 kickers. And I will explain over the next few slides the arrangement of these BPMs and kickers. So in order to explain how this feedback system works, we first have to look at what path the electrons take inside the accelerator. So at most conventional accelerators, we use what is known as a 4-door cell. So the main element that is present over and over again in these kind of accelerators is a quadruple magnet. So on the left over here, you can see a diagrammatic representation of a quadruple. So the electron beam is going straight into the page in the middle of this figure. And then we have 4 poles, hence quadruple, which have 2 north poles and 2 south poles. And in black, you can see the magnetic fields between these poles. When you have a charged particle traveling through a magnetic field, it will experience a force in the direction shown by the arrows. So the observation here is that in the horizontal plane, the beam is being focused, whereas in the vertical plane, the beam is being defocused. And this is inevitable. It will always focus in one plane and defocus in the other plane. So on the right over here, you can see the sequence of quadruples that are placed along the accelerator. So we will start off with a magnet which is focusing F in the horizontal plane and defocusing in the vertical plane, just as is the case in this drawing. And then the trick in these accelerators is that soon afterwards, we place another accelerator, another quadruple, which is rotated by 90 degrees around the beam axis, such that now we have a defocusing quadruple in the horizontal plane and a focusing quadruple in the vertical plane. And this sequence is iterated, so we have focusing, defocusing, focusing, defocusing, and the overall effect is that the beam is focused. And this type of sequence quadruples is referred to as a photo cell. So the outcome of this focusing is that the particles are contained within a beam envelope that changes in size. So we start off at the focusing magnet, and this red line over here shows the envelope of all the particles that will be going through. Because this is a focusing magnet in this plane, the envelope now shrinks because the beam is being focused in this plane until we reach the defocusing magnet, and then the envelope increases in size. But it is important to note that the particles themselves follow a sinusoidal trajectory through the accelerator within this envelope. And when you solve the equations of motion, the trajectories of these individual particles obey this formula, which is basically the cosine of a phase multiplied by an amplitude. And now I'll just briefly look at each one of the terms in this equation. The amplitude of this cosine oscillation is a function of beta. And beta is the size of this envelope, and beta changes with the longitudinal position along the beam. So basically, we have a sine function whose amplitude changes along the accelerator according to the size of beta. Another thing worth noting is that the phase of this sinusoidal oscillation of the particles itself depends on S, which means that sometimes the phase advance goes more quickly and sometimes it goes more slowly along the accelerator, depending on the strength of the focusing magnets. But basically, the oscillation of the individual particles of these blue traces is a cosine function. It's a sinusoidal oscillation, which is what I will show on the next slides. So just to simplify, we can see that the oscillation is just sinusoidal. But the starting phase of this sinusoidal oscillation can vary because we have this phi0 parameter, which is the phase at the beginning of the accelerator. So you can see that the individual particles all follow a sinusoidal trajectory, but the initial phase, the starting phase of the oscillation is different for the different particles. And we need to be able to correct the trajectory of each one of these particles, regardless of their starting phase. So let's take the example of the first trajectory I showed. And then, as I said, we will need two kickers in order to perform the correction. But in this case, we can just put a kicker, which is just an electromagnetic corrector magnet. We can put this kicker when the trajectory of the particle at the same place that the trajectory of the particle is crossing the 0 point. So we put the kick over here, and then we apply a kick to this particle, and now we can arrange, basically we can kick in such a way that the particle is now going along the axis, which is exactly what we want. So for this starting phase, we can make a very good correction. Now imagine this other particle that is going at a later phase. Then, because it is going through kicker K2, at this point, we can just kick the beam over here, and now it is going on axis. So for both of these particle trajectories, we can either use K1 or K2 in order to perform the correction. But of course, the phase could be any phase, and therefore, for most situations, we will have to perform part of the kick at K1 and the remaining part of the kick at K2 in order to then correct the trajectory of the beam. But the important observation is that regardless of the incoming phase of the particle, if we have two kickers located as shown here, we will be able to correct the position and the angle of the outgoing beam. So now let's look at where we should place these kickers. So the separation of these kickers actually has to be 90 degrees phase advance between the two locations. So you can see that the sinusoidal oscillation goes to 90 degrees between these two kickers, and this is the optimum separation of the two kickers in order to be able to correct the incoming phase. Now the next question is, where do we place the beam position monitors? So just for historical reasons, in our group, these monitors are called P2 and P3. But the point here is that the first beam position monitor, the optimum location for this monitor is 90 degrees phase advance after the first kicker. And the reason for that is because then on applying the kicker, we can get a full range of positions at this BPM. So we say that the BPM is most sensitive to the effect of the kicker if the BPM is located at this place. The other BPM would be located 90 degrees after K2. So this is our arrangement of the two kickers and the two BPMs in order to get a full coverage correction regardless of the incoming phase of the particles. So we now go on to the machine at which we performed our experiments to demonstrate that the feedback systems work. So this facility is called the Accelerator Test Facility, ATF, and it is located in the lab called KK in Tsukuba in Japan. It has two main goals. One of them is to have a very small beam size, and that is important in order to get a lot of particle collisions. And the second one is to have a very stable beam, which is the work that we were working towards as part of this feedback system. So you can see this accelerator over here in the picture on the bottom, and the beam is going from the right to the left. And you can see all of those quadrupoles that I was talking about, and the sequence of these quadrupoles is focusing, defocusing, focusing, defocusing, as I discussed before. I'll quickly give you an overview of what this accelerator looks like. So the electrons start from a gun in the bottom left of this figure, and then they are accelerated up to an energy of 1.28 GeV using a linear accelerator. The electrons then go in to this damping ring, and this damping ring is basically used in order to reduce the beam size of the electrons through a process of synchrotron radiation emission. Once we get a small electron beam, then we can extract the beam into the extraction line, and then the beam continues down what is known as the final focus to reach this final point here known as the model interaction point. So ATF only accelerates electrons and not positrons, and therefore all our experiments were just on the electron beam. We didn't actually obtain any electron-positron collisions. But the electron beam is sufficient in order to demonstrate that we can get the electron beam properties that are required for a successful operation of the ILC. So our feedback systems are concentrated within this extraction line and final focus. So just some quick points about ATF. ATF can be operated with trains of 2 bunches, and this is useful in order to obviously demonstrate that the feedback works bunch to bunch, because we can measure the first bunch and correct the second bunch. And actually, ATF can also be operated in 3-bunch mode, so we can show that the correction can be extended to a 3rd bunch, and therefore it should be able to continue regardless of the number of bunches. The separation of the 2 bunches can be adjusted up to 300 nanoseconds, which is comparable to the bunch separation at the ILC. It's actually more challenging than at the ILC, which is 500 nanoseconds. And our prototype feedback system works in the same way that it would work for the ILC, which is that it measures the position of the first bunch in any train, and then it corrects the path of the second bunch. And the repetition frequency, so the train-to-train frequency at ATF at this time was 3 Hz. The results that I show here were obtained as part of the feedback on nanosecond timescales group font, which I introduced at the beginning of the presentation. And we're aiming for nanometer level beam stabilization on nanosecond timescale, hence the name of the group. I will now show you the experimental setups that we were using at ATF. So on the left, you can see the beam line, and over the following slides, I will populate the beamline elements that we have over here. So starting off with these 2 BPMs that I said for historical reasons were P2 and P3. These are strip line beam position monitors. Basically, they consist of a strip along the top and a strip along the bottom of the beam position monitor. And when the electrons go through, they induce a charge on these BPM strips. And if the beam is closer to the top strip than to the bottom, then we can infer that the beam is above 0 in the vertical plane. And that is the mechanism that is used in order to then subsequently extract the position information of the beam in the BPM. The actual data processing, signal processing from the BPMs is done using these analog processors. The reason for the analog processors is because it is faster than having a digital system, and latency is critical for our system. And these BPM processors have a demonstrated latency of only 15 nanoseconds out of the 500 nanoseconds budget that we have for the whole system. And then we also have a second type of BPM, which is a BPM located in the IP region, which is a cavity BPM. It's a different type of BPM, which can achieve better resolutions, but it also comes with a processor that, as you can see, is much more complex and where the signal levels have to be very carefully adjusted. The signals, both from the BPMs P2 and P3 once they're processed, and from the IPB processor, are then digitized on a board. But this board is based on a field programmable gate array. So FPGAs, as they're referred to, are programmable logic. So they also are very fast. They're faster than using computer chips on a computer. Each board can take 9 input channels and can produce 2 output channels. And these output channels are once again analog signals that are sent to a custom-made amplifier produced by a UK company called TMD. And the output from this amplifier is used to operate the kickers. So to operate kickers K1 and K2, which I introduced before. And we also had an additional kicker called IPK in the IP region. I will now talk firstly about the upstream feedback system, which is basically represents the system that I described to you before. It consists of 2 beam position monitors, which are used as inputs for the feedback, and 2 kickers, which are used to apply the correction to the next punch. Just worth noting at this point is that we have another stripline BPM located 30 meters downstream, which we can use in order to monitor if the correction has been successful or not. These are the results that I obtained at the time of writing my PhD as part of the font group. And further work has been done since then, and these numbers have actually slightly been improved since then. But these are the numbers that we obtained at the time. So these plots over here show the distribution of the position of the beam at BPM P2, at BPM P3, and at BPM MFB1FF. It is the distribution of positions over many trains. And we had trains where the feedback was on, which were interleaved with trains where the feedback was off. So these results are for the first bunch in each train of 2 bunches. And you can see that because the feedback only measures the first bunch, but does not correct the first bunch, then the distribution of the positions of the beam for bunches with feedback off and feedback on are the same. The spread of this distribution, which is referred to as the jitter, the IMS spread of the distribution, is the same when we have feedback off or when we have feedback on for each one of the 3 beam position monitors. And this is because we're looking at the first bunch in each train, which is never correct. But now the situation changes completely for the second bunch, because the second bunch in each 2-bunch train is corrected. It is corrected when we turn the feedback on. So for the occasions where the feedback is off, where we perform no correction, we have a position jitter of around 1.7 microns. But when we turn the feedback on, the spread of positions over many trains is much smaller for this second bunch. So you can see that the spread here, the spread in beam positions over many 2-bunch trains is reduced by a factor 3. And the performance, the level to which we can reduce the spread of positions for the second bunch is limited by the BPM resolution, by how well we can measure the position of the first bunch in the first place. So a lot of work was done in order to try to improve the resolution of the BPMs in order to get the best possible feedback performance. Another interesting way of looking at the results is that, as I said before, because the 2 bunches are very closely separated, they're only 500 nanoseconds apart, there's no time for the accelerator to become misaligned between 2 consecutive bunches. Therefore, if we measure the position of the first bunch, this should be very, very similar to the position of the second bunch within any given train. So we say that the correlation of the bunch to bunch, or bunch 1 to bunch 2, is very high. This is what these plots over here are showing. So the points in blue show for each train, they show on the horizontal axis, they show the position of the first bunch, and on the vertical axis, they show the position of the second bunch. And you can see that there's a very strong correlation of 97%. The feedback uses the information from bunch 1 in order to correct the position of bunch 2. So the feedback acts to center the beam for all of the incoming bunch 1 positions. So you can see that when the feedback is on, which are the points in red over here, we have a spread of positions for bunch 1, but then regardless of the position of bunch 1, we always set the position of bunch 2 to be the same value. And actually, the mathematical result is that the correlation between bunch 1 and bunch 2 is removed. So the correct feedback operation shows that we go from a very high correlation bunch to bunch when the feedback is off to a correlation of around 0 when the feedback is turned on. The subsequent data that we showed, and we also showed that this system is sufficient, is suitable for operation at the IELC, was published in a paper in PRAB in 2018. The other mode of feedback that we used at ATF was the interaction point feedback, where we only use one beam position monitor, which in this case is called IPB, to operate one kicker, which in this case is called IPK. Once again, we can see that for the first bunch in any 2-bunch train, the distribution, the spread of positions is the same for feedback off as it is for feedback on. But once we turn the feedback on, then the spread of position is reduced from 420 nanometers to 74 nanometers. You can see that there's a very significant reduction in the spread of positions, achieving a very stable beam of 74 nanometers. And the reason we could get these very small numbers is precisely because we were using these cavity beam position monitors, which have an outstanding resolution. Once again, I can show you the correlation plots between the BPM position for bunch 1 and bunch 2, and the feedback goes from having a very high, the feedback takes the very high correlation when the feedback is off and converts it to a correlation of around 0 when the feedback is on. Once again, we published the results from these cavity BPMs as an input to the feedback loop, and this was published this year in a paper, once again, PR AB. So to conclude, I want to emphasize that a linear collider must have fast position feedback systems. And the work that we did in the font group and that we demonstrated at ATF shows that these systems would work and would have the required latency and resolution in order to be operated at, for example, the International Linear Collider. So in this presentation, I showed you two fast feedback systems, both of which are bunch to bunch. One of them is the interaction point feedback, where we use one beam position monitor to operate one kicker. And the other one is the position and angle feedback, which produces a correction that then propagates along the accelerator. And this feedback system requires 2 BPMs and 2 kickers. So thanks a lot for your attention. Thanks also to my group in Oxford and to our colleagues at ATF. And now I can take any questions that you have in English or Spanish.
Muchas gracias, Neven. Muy interesante. We're gonna take questions, and it can be Spanish or English. I have the feeling that most of the people here speak English, and I don't know, Enrique, how is your Spanish? But so maybe we continue in English if you like. And well, if anybody has a question, please just jump ahead or raise your hand. But in the meantime, I will ask one question. Just when I mean, I understand that the difference between the strip line kickers and the strip line beam position monitors and the cavity monitors is you have to have pairs for one of them, and you can use a single one for the interaction point one. But when exactly do you need to use one, or what are exactly the trade-offs? Because it seems to me like both are within the latency budget that you need. So what are the pros and the cons essentially?
That's a very good question. So yeah, in the interest of simplicity in this presentation, I showed the 2 BPM system using the strip line and the 1 BPM system using the cavity BPMs. But actually, you can use, it's interchangeable. So you could use 2 cavities for the 2 BPM system, or you could use 1 strip line for the 1 BPM system. So the main difference between the cavity BPM and the strip line BPM is the performance that they have. So the cavity BPMs have a very good resolution. So that means you can measure the position of the beam very accurately. But the problem with the cavity BPMs is that they have a very small dynamic range. So you can only measure the position of the beam in a very small range of positions. So the good news for the ILC is that the strip line BPM is sufficiently good as an interaction point feedback system, as an as a BPM for an interaction point feedback system. So for the ILC, the plan is to use a strip line beam position monitor because they are more flexible, they're more they're easier to use because they have a wider dynamic range. So if you want to have the best possible resolution, but you constrain yourself to a small dynamic range, then you can go cavity BPMs. But otherwise, most accelerators use strip-line BPMs around the world these days.
Thank you. I see that Bruce has his hand raised. Before I give him the chance to ask, just a quick follow-up on that question. Do you have a feeling for the cost difference between the strip-line VPM system and the cavity VPM system?
So I don't know the numbers of the cost, but I can tell you from our experience at ATF, the cavity BPMs are much harder to manufacture. And the reason they're hard to manufacture is because it's a cavity it's similar to an accelerating cavity, and the dimensions have to be very carefully adjusted so that you get an RF wave of exactly the right frequency. And if you have the wrong frequency, then because the way the signals are processed later, you will not actually get good results. So it has to be, the frequency has to be spot on. So in our experience, we had to remanufacture many times. And there's also a second problem with the cavity BPMs. Because they have a very small dynamic range, you also need to be able to position the BPMs very accurately in the first place. So there's a lot of constraint on the positioning of the BPMs. So basically, from our experience, operating with cavity BPMs requires much stricter machining tolerances, and therefore I suspect it will be more expensive. For strip-line BPM, it's more relaxed. You just need 2 strips which are placed inside the beam pipe. So I suspect they would be cheaper.
Yeah, that sounds reasonable to me. Thank you very much. Bruce, please.
Okay, thanks, Neville. This was a very nice talk. I have a question about the resolution of the BPM. Can you tell me a little bit about that?
Yes. So, yes. So I'll start with the strip-line BPM. But the question is, do I have numbers? Yes. Okay. So, so the numbers at the time that I was writing my PhD thesis, the number that we achieved was 300 nanometers. And this is at the charge. So the other important thing when you talk about BPM resolution is the charge at which you're working, because the more charge you have, the bigger your signals and the better your resolution. But the charge that we were working at was around 0.5 times 10 to the 10 electrons per bunch. And for that charge, we were getting a resolution of 300 nanometers. And then since then, we improved the processing, so we have higher signal levels. So I think the best number we got for the strip-line BPMs was 150 nanometers. With the cavity BPMs, the number, so I don't have the number here, the number that we got during my PhD was 50 nanometers, and I think it has been improved beyond that. So a strip-line cavity BPMs intrinsically will give you a better resolution than strip-line BPMs. So the numbers that we had at the time of writing my thesis was 300 nanometers for a strip-line and 50 nanometers for a cavity BPM.
Okay, thank you. One more question. I mean, you seems like the dynamic error misalignment is the main concern, right?
Yeah, I can explain more about it. Yes.
So the issue is like this is a particular issue in Japan when the number of earthquakes is a lot. So you want to put it here, and so you have a kind of comment about that?
Okay, so that's actually quite interesting. So there's 2 different things I want to say. So one of them, somewhere hopefully in the yes. So at many accelerators around the world, this is a reason for concern. So this has been measured at different labs. And so what this shows is the RMS motion of the ground, depending on which frequencies you integrate. So you start at high frequencies and then you go to lower frequencies. And basically lower frequencies means longer time periods. And basically the longer you wait, the more things will move. So you can see that for different locations where this was measured, you get different amounts of motion. So the most stable that was measured was in a salt mine, and that's underground. And then you can see that actually, depending on the geological structure, you get different vibration levels. So the interesting thing was in Japan was, of course, there was a concern that because it's a seismic location, that it could be an issue. But as far as I remember, the location that was chosen for the ILC was actually in a granite mountain. So the idea was that the accelerator would move as one piece. So the main problem that we have is if different parts of the accelerator are moving by different amounts. So my understanding was that the level of vibration in Japan was actually not the highest you could get. I think it was higher at Daisy in so from the measurements that they did. So the first aspect is, yes, they have considered the ground motion that they have in Japan, and even though it's a seismic location, it was actually the ground motion in the absence. Of course, when you have an earthquake for the seconds that you have the earthquake, of course this does not apply. But in normal conditions, it's actually more stable than other locations. That was one point. The other point was this thing of the positioning of the BPMs. So the challenge that we had was these cavity beam position monitors that we had were actually welded to each other, because that was the way that they were manufactured. So we had two cavity beam positions welded to each other, but the dynamic range is only a few hundred nanometers, a few microns. So so wait, do I have a number for the dynamic range? Anyway, the resolution, no, I don't have the number, but the dynamic range is quite small. So I think it's on the level of microns. So the problem is, if your two cavities, which are welded to each other, are misaligned relative to each other, then you can never get the beam through the center of both. And you can never, we were actually in a position where you couldn't get it through the dynamic range of both at the same time, which obviously is a problem. So generally, yeah. So even having a situation where you have two cavity BPMs that have been welded together in a lab, which you would think is like will guarantee you perfect alignment relative to each other, even that was challenging. So imagine if you have like detached BPMs which are independent to each other. So I don't know whether it answers your question, or maybe we can take more details if you want.
No, I think that it's answered quite nice. And just maybe the last, if they allow me, about the static error, because I mean, it seems like this work more for the point of view of the dynamic. I mean, when you have this kind of fluctuation between train and punches. But when you, well, like for instance, like the case that you mentioned, you have a misalignment on the cavity monitor. So how you can align in that case?
Yes,
I mean, this is more like a kind of static error.
Yes, that is a very good question. And as you said, this work was precisely trying to do the dynamic errors, and that was why the latency had to be quite small. So in general, in linear accelerators, yes, a lot of effort goes into aligning the whole machine in the first place. And depending on the design, in that sense, click was particularly challenging because the beam was particularly small in click. So basically, one approach that is used for centering at accelerators around the world is that you look at the effect that the quadrupole has on the beam. So what you do is, if the beam is going exactly through the center of the quadrupole, then when you scan the quadrupole strength, you will see no deflection on the outgoing beam on the quadrupole. Then you know that the beam is centered through the quadrupole. If when you change the quadrupole setting, the beam gets deflected, that means the beam is not on axis in the quadrupole, it's getting a dipole component to the kick. And then what you have to do is you have to correct the path of the electrons, or whatever the path is. And depending on the accelerator, the most typical thing that you do is that you use corrector magnets in order to get the beam through the center of the quadrupole, so that when you scan the quadrupole, the beam doesn't move. If you go for a very fancy accelerator design like CLIP, then all the quadrupoles were on movers. So then you could physically move the quadrupole until you have the beam going through the center. But that is very costly and requires a lot of precision on the position of the movers. So the most typical thing is that you use corrector magnets to steer the beam, and you typically use the quadrupoles, scanning the quadrupoles, and reaching a point where changing the quadrupole strength does not affect the position of the beam for centering. This is, I think, used in many accelerators around the world.
Okay, thank you very much.
Thank you, Neven. Thank you, Bruce. I don't know if there is any other questions. If no, I have a very silly question, because when you're showing the diagrams for the dispersion of the position, yes, it's very, very clear when you go exactly when you have your feedback on, especially with the cavity, how narrow is your jitter, your dispersion. However, how important is that the average, the position is actually not the same in the case of off and on?
Yeah. Okay. So actually, in the feedback system that we were using, you could just add a constant kick value as a number in the control system. So you could actually arrange to move the beam to the other place quite straightforward. So basically, you apply a constant kick to all the punches, and then you will end up here. So actually, yeah, I could have picked some other ones where we actually did that, but most of the time we didn't worry too much about it, because we knew that it would be easy to just change the position of the second beam.
Yeah, exactly. That was my question, is because in this case, I guess the most important factor was the jitter and not precisely the position. So okay, I'm just not used to.
No, of course not. It's a very good question, and it would, yes, the goal would be to end up in zero position. So you could fine tune the constant additional kick to get it on zero position, and that would be actually very important when you have collisions at an accelerator, because you would, it makes a big difference if if the number is correct or not, even though it's the easiest part to add a constant kick.
All right, thank you so much, Neven. I don't know if anybody else has any further questions or comments. If not, I want to thank again Neven for giving us his time and talking to us about his PhD research. And hopefully next time you can also tell us what are you doing at Max 4. So we would love to have you back at some point in the future.
Excellent. Thanks a lot. Muchas gracias.
Muchas gracias.
Hasta la próxima.
Hasta luego todos.
Yes.
Hasta luego.
Muchas gracias, Neven. Hey, Enrique. It's been a long time I don't see. Well, that's not true. I saw him I saw you in Melbourne last time.
Yeah, a long time to see.
It was nice for you to come by.
I told Enrique we were talking about you and other people from USPAS.
It was nice to learn a bit of diagnostics from Linux, because I'm only used to the storage ring ones.
Yeah.
Quite nice.
Yeah, it's quite different, no? It's also I'm not used to any of these things. So it's super interesting. I'm sure